Okay, we got chapter 14, some question discussion, problem solving. The first problem, yeah, this is the one that we discussed during the lecture. I said it's not uh, calories, it's kilocalories, and you can see the capital C that actually stands for kilocalories on the food label. And if it's 2,500 calories, kilocalories a day, then what is in joules and how much kilowatt hours that would be, and a fun question about how much would your energy cost per day if you would bought it from a power company. So 2,500 kilocalories. Kilo means 1,000, so you multiply by 10 to the power of 3. That becomes 2.5 million calories. And then converting that to joules, the conversion factor is what we got in lectures, about 1 to 4 joules for 1 calorie. And you end up with what? 10 million joules. 10 million joules, that's the amount of energy that your body needs for 1 day of activity. The ratio between kilowatt hour and kilocalorie is also here for your reference in case you ever wonder how you convert one to the other. You can see that those kilocalories canceled and you left with those kilowatt hours. That's only about 3 kilowatt hours, and at 10 cents per kilowatt hour, your food would only be 3 times, 10 cents, so about 30 cents. And of course, you can't feed yourself on that amount of money, especially with current inflation prices. You can see that uh, there's no way to just charge yourself through the power outlet like a robot and be fine with that for the day. You need to pay a lot more for the food that you consume. Okay, that was a fun stuff. On to the real physics world. How many joules and kilocalories are generated when you use brakes to bring just a regular car to rest from 95 kilometers per hour? First of all, no kilometers per hour. You have to convert to meters per second. And hours in terms of seconds, you can see the conversion. And kilometers, you don't want kilometers, you want meters. Kilometers cancel, you're left with meters. So 26, some change in terms of meters per second. Here we are with the energy balance. So what we lose is kinetic energy, and what we convert that into is the thermal energy, the heat, the energy transfer from energy of motion into energy of braking. And if you uh, think about friction, that would be the thermal energy conversion. So 1/2 mass of the car is given. The change in energy would be all the way to 0. So you're going to convert the whole amount, the initial velocity squared. So we are talking about what? 450,000 joules for any such process. So every time you apply the brakes to slow down from 95, that's like about 100 miles, it's like 60 miles per hour. You actually convert hell of a lot of energy from your energy of motion into just heating up the environment through the process of braking, using the brakes. So kinetic energy is converted into thermal energy. This is your energy balance for this problem. Oh yeah, and if you want to convert into kilocalories, then you use the ratio that we just discussed. So what is it? 110 kilocalories. Once again, do not do calories. Forget calories. Don't you ever do any calculations with calories. Only System International units, which are joules. Okay, this is more of what you should expect for the test. So pay attention, try to understand what's going on. What's the equilibrium temperature when a certain amount of copper at a certain temperature is placed into a calorimeter made of aluminum, and there is water at 12 degrees Celsius. So this is what's going. We have cold water, and you put a very hot piece of metal into it. Of course, the metal is going to cool down, and the water is going to heat up. So your energy balance would be heat lost by the copper is heat gained by the water. Or you would say what is lost by copper and gained by the aluminum calorimeter, because calorimeter is also going to heat up, and the water, that is equal to 0. So what's lost is negative, what's gained is positive, and the overall energy balance is 0. 0 change for the total amount of energy. So lost by copper is the mass of the copper, specific heat for the copper, and the difference in temperatures. Of course, we don't know the equilibrium temperature. We want to solve for the equilibrium temperature. So this is our final equilibrium temperature. Take away the initial temperature of the copper, which was given in Celsius. You cannot do Celsius. You have to convert to Kelvin. So 245 plus 273. This is your Kelvin value for the initial temperature of the copper. Mass of a copper is given. Be careful, that's grams. You have to convert those grams into kilograms. And for copper, you take a look at the table with specific heat, and you'll find that the specific heat for copper is 390 joules per kilogram per Kelvin. So this is the green part. That's what is here. Next, we have the calorimeter made of aluminum and water. So first of all, we have water, the mass of water, the specific heat for water. Be careful, water being liquid. We have 12 degrees Celsius. It's right. It's in between 0 Celsius, which is freezing point, and 100 degrees, which is boiling point. So we are in the liquid phase. And for liquid phase, you have to go with 4186 value. There's no ice. There's no steam. It's all liquid. And it says 825 grams. So you have to convert those grams into kilograms. And once again, it's the equilibrium temperature we're looking for. We don't know it, but the initial temperature of water is given. It's given as 12, but you have to convert to Kelvin. So you plus 273, and you're going to get 285 degrees Kelvin for the initial temperature of water. And then there is aluminum calorimeter. The calorimeter is the device that contains water, so you have to consider heating up of that calorimeter as well. For the ideal calorimeter, once again, you don't have to consider any change in temperature, but for real world problems, definitely you have to think about calorimeter by itself. It has to heat up and to a certain amount. How much? Not so much. The mass of a calorimeter is given. It's 145 grams. Convert that into kilograms. Aluminum has greater, well, it's 900 units for the aluminum from the table. The equilibrium temperature is the unknown, and it's also at the room temperature together with water. So the initial conditions for calorimeter is same as water. Water was at 12 degrees Celsius, which is 285 Kelvin, and the calorimeter is also 285 degrees Kelvin starting temperature, because it's 12 degrees Celsius. So this is the energy balance. Lost by copper, gained by water and calorimeter. Boom, you solve for the equilibrium temperature, which is the unknown. You open up the paren, combine like terms, do the algebra. You should be getting this value, which makes sense. It's going to be a little more than the initial. If initial is 285, then your water heats up to 291 degrees. That's more than 285. Once again, makes sense. Water heats up. Okay, this was the easy case. Let's see what we have next. Once again, we got some sample of a certain substance at a certain temperature, and then once again, aluminum calorimeter, and then some water inside, and the final temperature is now given, right? We just solved for the unknown temperature at the final. Now the temperature is given, and you have to figure out the substance. What kind of a substance is that? And see how it says specifically no water boils away. That means there is no phase change for water to consider. No water boils away. No need to account for latent heat and phase changes. So we don't know what the substance is made of, but we know that it's going to be cooling down. So some heat is lost by the substance, and then the same amount is gained by the calorimeter and water, and the glass thermometer, which is also used here. You have 17 grams of glass at a certain temperature, so you have to consider that as a part of the system that will be heating up. So what is lost by the substance is the mass of a substance, specific heat of a substance that we're about to figure out and find what is the material. And equilibrium temperature, it's the final temperature, which is 35 degrees Celsius. You have to convert to Kelvin. And the initial, which is 330 degrees Celsius, which you convert into Kelvin. And you get the coefficient of 63.4 with a negative because we are losing it, right? Don't ignore the negative. You need this negative for the equation balance. That's the amount of energy lost by the substance. What's gained by the calorimeter is the mass of the aluminum, specific heat of aluminum. We did that before. The equilibrium is also 308, same as like it's your final temperature for the thermodynamic system in general. So 35 degrees Celsius converted into Kelvin. Take away the initial for the aluminum. Initial for the aluminum is 10.5 Celsius. So convert the 10.5 into Kelvin. That's what you're going to get. Do the math, and you get 2315 joules gained by the calorimeter. This is what's gained by water. Water is cooling down. No, excuse me. Water is heating up from the initial to final. And for water, you definitely need the liquid coefficient, the 4186. And the mass of water is also given. It's 195 grams that you convert into kilograms right there. And you do the math and you get about 19,000 joules, which is a much greater compared to what the calorimeter gets. See how like calorimeter gets 10% and the rest is pretty much water. 90% is the heating up of water. That's why for ideal calorimeter, you can just, ignore it and just add everything for water. And the glass thermometer, I want to point out the overall change in terms of energy balance is just 350 joules. What's 350 versus 19,000, right? There's literally just, pocket change. You can ignore it, but we're not going to ignore it. We're just going to include it in our energy balance and get the value for the specific heat of glass, mass of the thermometer that is given as what? 17 grams. So convert those grams into kilograms because we're doing System International. And once again, final temperature, take away initial in terms of Kelvin. Do the math, you will get 350. And this is what's lost by the substance. And those three things, that's what's gained by the calorimeter, the water, and the glass thermometer. Overall change in energy is 0. So solve for the unknown specific heat of a substance. Boom, you have 341 units. That is, oh, and now you actually have to go back and see what does that correspond to? I'm gonna, how do I look it up from the lectures? 341. Okay, I need the book real quick. No, not the book, but the lectures. Chapter 14. Let me see what 340 correspond to. Okay, we have copper at 390. And we have, yeah, it looks like it's copper mixed with probably a little bit of lead, something like that. Anyways, back to presentation. So 340, this is really close to be the copper with a little bit of lead, like some kind of an alloy. The point is, you can do such an experiment in real life, and let's say you don't know the specific heat of a certain element, you can figure it out from this kind of an experiment. That's exactly how we produce those tables that you look at to solve problems on thermodynamics. This is the kind of experiment that you do to figure out the unknown specific heat of a certain substance. Okay, now we got iron, a boiler of certain mass, and there is water at like room temperature. And then there is a heater that supplies energy at a certain rate. See how it's kilojoules, be careful, it's not just joules, but kilojoules. And it's not per second, it's per hour. And the question is how much time to take the water to reach the boiling point and then to convert it to steam. So first of all, what is the what is the energy per time? Energy per time is what we call the power. So what you have here given is the power for that heater. And for energy, if you want to figure out how much energy is transferred at the certain rate, you multiply the power by time. Or if you want to solve for how much time, you have to divide the energy by power, and energy would be the heat this time. And the heat is also Cm delta T, the specific heat times the mass times the change in temperature. So you can solve for the time from, once again, the definition of power, and which would be energy divided by power, and heat by itself. The energy transfer is the Cm delta T formula that we discussed during the lecture. So Cm delta T for boiler, Cm delta T for the water inside the boiler. That's the energy that we're going to need to heat it up to a certain temperature. And then the power, we don't want kilojoules, we want just joules. So there is 1,000 to 1 conversion factor. And we don't want hours, we want system international units, which are seconds. So 1 hour is 3,600 seconds. Do the math, plug in the values for the iron for the specific heat of boiler. Mass of a boiler is given. The change in temperature is, let me see, it starts at 18 degrees Celsius, and you go all the way to the boiling point, which is 100 degrees Celsius. Convert from Celsius to Kelvin, so plus 273 for both. And you can factor out the delta T. See how you have delta T here and the same delta T there, so you factor out the delta T. From 18 to 100 degrees Celsius, so 373 Kelvin, take away 291 Kelvin. This is your water with a certain mass. This is the iron with a certain mass. That's the total amount of energy needed to transfer to that system, so it is heated up to 100 degrees Celsius, which is 373 Kelvin. And divide by 16,000 joules per second. This is your power. This is the rate of energy transfer in a unit of time. Do the math, you will get about this many seconds, which corresponds to about 4.5 hours. And that's a lot of time. But if you will consider boiling water to be transferred into gas, remember, it takes a hell of a lot of time and energy to convert water into gas. And this is the proof for this fact. This is now the formula. There is no temperature change. The water was at 100 degrees. The gas stays at 100 degrees as well. And now it's the vaporization, it's the latent heat of vaporization, not fusion. Remember, we did the fusion thing in the lecture. Now it's the vaporization because we're going not from solid to liquid, but from liquid to gas. So it's a different value for water. The mass of water is still there, and the rate is still there. This is the same boiler and a heater. So see how much more of a value for the latent heat compared to 3.33 times 10 to the fifth. Remember, it was 333 kilojoules for the specific heat, and the latent heat is what? It's about 10 times more of a value, which produces much more time for you to wait before you convert water into vapor, into gas. And overall time, see how it's 4.4 hours and this many hours, 33 hours for the complete transfer. Think about it, 33 hours to wait for that water to become the steam. This is why our power plants, the coal power plants or even nuclear power plants, they all work on the heating up the water to steam, and that takes a hell of a lot of energy and time to generate electricity. It used to be a good option, not anymore. We have better options as solar panels and windmills. Please consider getting those for your household and investing in the market. Solar panels is what we definitely need for future. Okay. Okay, now the crime scene. We got investigators, detectives. There's a lead bullet that was stopped in a door frame and melted. The key word is melted. Melted means there was a phase transfer from what? It was a solid, and now it's liquid. If there was melting process, that's your fusion from solid to liquid. So there is definitely a phase change for this problem as well. It was shot at room temperature. And what's the muzzle velocity of the gun? Once you figure out the initial velocity of a bullet, you can tell what kind of gun was used for the crime. And that's the first thing detectives want to know, what kind of a gun was used. So that's what they would do and measure and do the calculations. So let's play detectives. We got the kinetic energy of a bullet, 1/2 mv squared, which was transferred into thermal energy. There was energy transfer from room temperature all the way to the melting point for lead. And then also that bullet has melted. So it was all the way from the room temperature to melting point, and then the lead has melted. So this is your latent heat of fusion. That's what you will use to do the calculations. Fun fact, you can see the mass cancels, and it's not about the mass of a bullet, even though it's given, but just the thermodynamic parameters that you can find in a table. So the specific heat for the lead to heat it up to the melting point from the initial room temperature. And then the latent heat of a fusion. Fusion is your solid to liquid or liquid to solid. It's not vaporization, right? We just use vaporization for water, converted into gas. Now it's back to solid versus liquid. So it's latent heat of fusion. And let's plug in the values for what's given and for what's missing. For the lead, specific heat is given in the table. Melting point for lead is 600 degrees Kelvin, and room temperature was 20 degrees plus 273. That becomes 293 for the Kelvin scale. And latent heat of fusion for lead is, 25,000 joules per kilogram. Do the radical out of that because it's V squared, and you get 360 meters per second. That's a certain muzzle velocity corresponding to a certain gun that detectives will easily figure out because they have a good knowledge of different muzzle velocities for all of those guns. Every time a new gun enters the market, the very first thing the manufacturer provides is the muzzle velocity, the initial velocity for a bullet that leaves the gun. Okay, now the microwaves. Did you know that you can heat up everything in a microwave that has water in it? Let's just do water by itself. And the maximum setting, it raises the temperature from room temperature to boiling point in 105 seconds. What's the rate of energy put? So what's the power? What's the power output of the oven? The power output is energy transfer with respect to time. And energy transfer is Cm delta T here. There's no phase change for now. It's just heating up water from room temperature to boiling point without any transformations in the phase. So just Cm delta T. The liquid water is 4186. We did this coefficient before. Then it's the mass of water, which is 250 grams. Be careful, don't do grams convert to kilograms. And the temperature change from 20 to 100. So plus 273 plus 273, that gives you this many Kelvin degrees of a change. And the time frame is 105 seconds. Good news, it's already in System International Units. So 105 seconds, that's what we get. Do the math. Boom, you have 800 watts. I'm pretty sure you've noticed your microwave has a certain wattage printed on it. The manufacturer provides you with that information. So knowing that information, you can predict how much time it's going to take to heat up something to a certain temperature. All you need to know is the specific heat for that object and how much of a mass that object has. And then the second part, it says same power input, and the sum of the water will boil away. Boil away means what? It will be converted into gas. So there is a phase change if you operate it for 2 minutes rather than 105 seconds. Well, 105 seconds is what? 1 minute and 45 seconds. So extra 15 seconds of operation, how much water will boil away, will be converted into steam, into water vapor. One, two, sorry, headset turned off. So for the remaining 15 seconds, the energy input will vaporize the water. That's what we say here. And for vaporization, it's the latent heat of vaporization. No more fusion. Back to vaporization. Your liquid becomes the gas. And it's the same power input multiplied by 15 seconds of operation with respect to the latent heat of vaporization for water. That's the amount of water that will evaporate, which is 5.3 what? Grams, because if it's kilograms, kilo means 1,000, but you have thousands. So 10 to the negative third and 10 to the positive third, 3 kind of cancels, and you're left with 5.3 grams. Oh, and that is it for the problem solving. So you can see all the phase changes problems. Really want you to focus on those. Go over those on your own. Do the math with calculators. Make sure you get the same numbers. And you will see something like that on the test. The easy case, when you don't have any vaporization or fusion, was here. See, no water boils away. And harder cases, when you have phase changes, are towards the end of the file. So make sure you cover both scenarios and you understand if there is a phase change or not and what you do in both cases.